Hello, it's Keith here, and this is lesson 5 of my Z80 assembly programming tutorials. We're going to be looking at some more of the Z80 instructions today, and we're going to be looking at ones relating to bit shifting and logical operations. These are commands that shift the bits around within a byte and even between multiple registers in some cases, and we'll see that. And also the logical operations, these are AND or XOR, things like that, that allow us to perform operations on sets of bits within our registers that are quite useful for some things we all want to do. So we'll go over to the code and see these in practical example as usual. Okay, so this is today's file. We're looking at 2021 lesson 5 today. So let's just fire this up with the first example. We'll be looking at RLC and RRC first. And these are commands that work with an 8-bit register that we specify after the command. So here we're going to be trying RLCA first and RRCA second. Now in this case we're working on the accumulator, and we've given the accumulator this weird test value here, and as always I would recommend you go to my website and download the example and try it out yourself. And the reason you will want to especially do that today is you can change the values in the accumulator here and see how this is affected on different values, so you can make sure you're clear in your head what exactly is going on. Now RLCA is rotate left and copy a bit to the carry flag. RRCA is rotate right and copies a bit to the carry flag. Now rotating is in this case referring to the bits. Now if we look first at RLC, if you look at this first line here, we had 01, 01, 0, 111. And what we've done here is rotated the bits to the left once, and each time we run this command we will shift by 1 bit. So you can see here that that top 01 has shifted to the left. So all of these bits have shifted to the left, and the top bit was a 0, and that has now become the rightmost bit 0 here. So you can see that if we just look at those two lines there, the starting point and after one rotation, you can see all the bits have shifted to the left, and the top 0 has now become the bottom bit. When we shift again, all the bits move to the left once again, and the old top bit was a 1, and that has become the new bottom bit there. So you can see that the one that was over here at the far left is now at the far right here. So that's how our bits are shifting, and you can see each time we're doing this shift to the left, the bits are moving around, and every bit that's pushed out of the left hand side reappears at the right hand side. And that means that after we've done 8 rotations, our ending value here, 01, 010, 111, is exactly the same as our starting value here, because we're rotating around within the byte and we're never losing anything from that, and we're never putting anything new in really. Now with this rotation there is a copy going on, and the top bit here is actually being copied into the carry flag, and we can, if we want, do something with that later on. We don't need to, of course. We can just use this command for rotating around the byte, but if for some reason we want to use the bits that were moved out of the byte from the left and brought back at the right hand side, they are also copied into the carry flag here. So you can see that this C here has come from the previous line's 1 that was pushed out and ended up back in bit 0 here. And you can see every time that the bit that's been pushed into bit 0 here was a 1, the carry flag has been set, and every time it's a 0, it's been cleared. Now that was RLCA, which rotated to the left. We can also use RRCA, which rotates to the right, and that's exactly what we've done here. We've taken this value here, rotated it once to the right, that's pushed a bit 1 out of the right hand side, and that's reappeared on the left hand side. Also it's appeared in the carry, of course, in the same way as before. And as we repeatedly rotate to the right, the bits that are pushed out the right hand side reappear on the left. And so again, at the end of our execution here, the value after 8 rotations is the exact one that we started with, because as I say, nothing new has been put into the byte and nothing has been taken out of the byte either. So that's how we can use these rotations. Now what I often use this command for is, quite often in our programming we might need to swap the top and bottom nibbles. Well, if you do a succession of 4 RRCAs, you will indeed swap the top and bottom nibbles, and as I say, nothing else is pushed in and nothing else is taken out. The carry is just a copy. The carry is never put into this byte, so the carry flag doesn't affect the contents of this byte as we repeatedly rotate, but there are other commands that the carry does have an effect on, and we can use it to our benefit, and we'll see that later on with RL and RR. Okay, so that's the first one, rotate left and rotate right. What we're going to look at next is shift left for arithmetic and shift right for arithmetic. Now these shifting commands are kind of intended for multiplication by 2 and division by 2. You see, if we look at our bits, if we get our calculator up here and we put a value of 1 into our binary here, which of course has a decimal value of 1 as well, well, every time we shift to the left, if we just shift to the left here, we've now got a value of 2. If we shift to the left again, we've got a value of 4. If we shift to the left again, we've got a value of 8. Left again, 16, and so on. And this isn't just for a single bit being 1. Any value at all will double whenever we shift the bit to the left. So here we've got a value of 20, and in the same way, every time we divide by 2, we're effectively shifting the bits to the right by 1. So if we shift to the left, we're effectively doubling the value in our register, but if we shift to the right, we're effectively halving the value in our register. Now this is fine for positive numbers, but when we're working in negative numbers, we need to make sure that the sign doesn't flip, and that means that all of our top bits need to be 1s. And now if we shifted to the right and we put a 0 in that top bit, then that would effectively flip the sign. So if I take my top bit here and I put in a 0, well, now the sign has flipped. It's no longer the same negative number. So we need to make sure that the commands we're working with, if we're working with signed numbers, will not change the top bit, and that the top bit always stays a 1 if we've got a negative number. And that's why we've got 2 sets of commands for working with shifting numbers. Now we've got shift left arithmetic and shift right arithmetic. And in this case, arithmetic actually refers to working with signed numbers. Shift left logical and shift right logical are designed to work with unsigned numbers, and we'll see the difference right now. So if we fire up our code here and we see these in action, so we're basically going to do the same thing as before. We've got a relatively random looking number here and a relatively random looking number here, and we're going to shift left for arithmetic here, and then we're going to shift right for arithmetic here, and we're going to see how these numbers change. Now we've started with our number here and we are now shifting to the left, and whereas before a bit that was pushed out was copied to the accumulator and also the bottom bit, that's a rotation, and this is a shift. Now a shift will not put the old bits that were pushed out back into the register. They will still go into the carry, so you can see that the bit 1 in that top line that was pushed out has ended up in the carry in the next line. The bit 0 has ended up clearing the carry there, and so on. You can see always that the top bit in the previous line has become the carry in the next line. But in all of the cases, the new bits are 0s, and this is effectively doubling the signed number in these values here. Now actually, because we're putting a 0 in, these will also perfectly successfully double an unsigned number in this case as well. The shift left arithmetic command is fine for a signed number of -128 to +127, or an unsigned number of 0 to 255. It will work just fine in both cases. The more important one is shift right arithmetic. Now this is designed for signed numbers only. So this will take a value of -128 to +127, and it will shift it to the right, and it will maintain the sign. So in this case, our starting value had a top bit of 1, and so as we shifted to the right, all the new bits that were added as the top bit were also 1. So this means that the sign, which was negative to start with because we had a 1 at the top there, and every time we shifted to the right, the new bits were also 1, so that the sign is still negative, and this is effectively halving a signed number here. And so shift right arithmetic is the correct command to shift a signed number, effectively halving it. Shift left arithmetic can be used for a signed or unsigned number. It will work just fine in both cases. So in that case, we were shifting to the right with a top bit of 1, and as I say, that is effectively a signed number. Well, what happens if we shift an unsigned number? So this one, almost the same, but we've got a top bit of 0 here. So this is effectively a value effectively under 128. Now if we are treating this still as a register containing a signed number, we want to still maintain the sign of this. And so in this case, instead of shifting 1s in, we're this time shifting 0s in, and that's because the new top bits will always be the same as the previous top bit. So when the top bit was a 1, all the new bits were 1s, but in this case the top bit is a 0, so all of the new bits are 0s. So this is maintaining the sign of the register. As I say, it's intended for a value of -128 to +127 in that 8-bit register there. So that's how we can use our arithmetic shifts to maintain a signed number as we effectively halve or double it. What about working with unsigned numbers? This is values, of course, from 0 to 255, where we will not want to copy that top bit, otherwise we will mess up our unsigned numbers over 128. Well, let's take a look. Well, first of all, we need to discuss a slight quirk of the Z80. Now, we're looking here at a command called shift right logical, which is for shifting unsigned numbers to the right, effectively halving them. But there is also an odd command called shift left logical. Now, this kind of command exists on a lot of other processors, and what it effectively does in every other processor's case is the exact same thing as shift left arithmetic, because shift left arithmetic will work fine for unsigned or signed numbers. It works exactly the same way on most processors. However, on the Z80, it's effectively an undocumented opcode which does not work as you would expect. What it actually does is it shifts new bit 1s into all of the new bits as we shift to the left. So the bottom bit that's being inserted into bit 0 here is a 1 in all cases, and this, for the logic of what shift LL should do, isn't correct. Now, I will warn you, I had become used to using this command in my code, and you think, oh well, that's fantastic, you know, it's if I need to push a bit 1 in there, why not use this? And that's to a great extent true. But the EZ80, if you ever need to use that processor, does not support this command. It's an undocumented command, and the bytecode that it compiles to has been reused for another purpose on the EZ80. So if by any chance you want to use that processor, you'd want to avoid using this command. It is supported on the R800. That's the processor of the Turbo R, the Z80 clone. It does support this command fine, but as I say, it's an undocumented command, and the EZ80 does not support it. So use it at your own risk, shall we say, but it does indeed push extra 1s in there. Now, shift right logical works in the way you would actually expect, which is to shift new bit 0s into our register as we shift to the right. So in this case, our top bit was a 0 anyway, but all the new bits, whatever that top bit were, is going to be a 0, and that's because we're halving an unsigned number every time we shift to the right in this case. So that's what we've done there. Now we will just confirm the rather quirky functionality of this. Let's try these alternate values here. So this time we're going to be testing a shift left command with a bottom bit of 0 just to see what happens, and this time we're going to be trying a shift right command with a top bit of 1 just to see what happens. Well, let's indeed see what happens and see if I'm telling the truth or I've got confused again. Okay, so well, this time what has our undocumented shift LL opcode done? Well, once again, it's shifted 1s in, so the ones that are being inserted have no bearing on the bottom bit or the top bit of the register. It's always a 1 that's inserted. And shift right logical, because it's decided to work with value unsigned numbers of 0 to 255, and we want to maintain that sign as we halve them, shifting to the right, the new bits are always 0s. And I think basically the shift left logical undocumented opcode is doing the exact opposite of the shift right one. It's shifting in the opposite direction, and it's inserting the opposite bit. It's inserting bit 1s rather than bit 0s. But as I say, a shift left logical type command on other processors would actually shift 0s into the bottom bit, and that's what it should do if the command was actually describing the function correctly. It's not a shift left logical, it's a shift left and push in a 1, as I say, an undocumented opcode that's not officially supported. So there we've looked at how we can rotate bits around a single register and how we can shift bits to the left and the right within an 8-bit register. But what about pushing bits into new registers? And also, what about if we want to work with signed or unsigned numbers, but we want to halve or double a value that's over the value an 8-bit number can support? Well, in both of those cases, what we want to do is we want to use a pair of registers, and we want to use rotation commands. Now, our previous commands that we looked at for rotation were rotation and copy to the carry, and these only shifted bits around within the register. But the rotate left and the rotate right command actually push the carry into the register, and so combined with another command, for example this case, the shift right arithmetic and the shift left arithmetic, the shift left or shift right arithmetic will push a bit out of the first register, the E register in this case, into the carry, and then the rotate command here will rotate that that bit that's in the carry back into the second register. And this has the effect, in this case, of combining these two registers into a 16-bit pair. Well, let's check this out and let's see what happens. Okay, so in this first case here, we've loaded a value of D6 into our DE pair here. So you can see D is starting at 0 and E is starting at D6 here. And then what we're doing here is we're going to repeatedly shift the E register one bit to the left for arithmetic, which means all of the new bits will be 0, effectively doubling the value in that register. But some of the bits are going to be pushed out, and they're going to be pushed out into the carry flag by this shift command. But then we're going to use our rotate left command, and this effectively takes that carry bit and rotates it into the D register, shifting all of the other bits in the D register to the left by 1. Now at the start our D register was 0, and then we are going to push one bit out, so this one bit will be pushed out of this register here. So you can see our E register has been shifted 1 to the left, and the top bit 7 that was a 1 has been pushed out, but that will be pushed into the carry and rotated into the second register, the D register, by the rotate left command here. So that bit 1 has been kept and moved into the D register here. That's the D register here. So you can see that is the result of the combination of these two commands. And the effect of this, if we repeatedly run this command, is that our DE 16-bit pair is effectively being doubled each time. And if we do it repeatedly, what we've actually ended up with is that we've effectively multiplied by 256 as a successive set of rotations. So our D register now contains the value our E register did. That's the value of D6 here. And you see that there. And our E register has contained a value of 0. So we've never actually lost a bit here. They've simply been shifted out that bottom register into that top register via the rotate command, with the added bonus that we've actually done something very mathematically useful. We've effectively repeatedly multiplied by 2 the 16-bit DE pair here via that pair of commands. Now you could also do this via an add command, but the rotate command is often quite a lot more useful, and as I say, you can do other things with it. Maybe we want to shift a bit 1 into the D register, or we could just set the carry and then use the rotate command, or we could clear the carry and do a rotate to shift bits 1s and bit 0s into our register as we need. And sometimes I've done that as part of a sort of keyboard testing routine. I'm maybe setting up a byte with different bits as up, down, left and right, and you might want to do something like that to shift the bits in as you test the corresponding keys of your keyboard. Anyway, that's what we've done with our shifts to the left. We're now going to do shifts to the right in exactly the same way with exactly the same value. So we started with the ending position of D6 in D and 0 in E, and again we're shifting this time to the right. All of our new bits this time are going to be, because we're shifting for arithmetic, all of our new bits are going to be bits 1 here because of the sign. And after we've repeatedly done these shifts, we have now got D6 in the E register, the low byte of the pair, and the D registers become all 1s because we're effectively treating this as a 16-bit signed number. But if we wished and we wanted this to be a 16-bit unsigned number, we just need to make a very small change to our code. We just take this shift right arithmetic and we change it to a shift right logical, and then we just run again, and this will work in almost the exact same way. The bits will be shifted out of D and rotated into E, but this time the shift right logical rather than shift right arithmetic is treating this as an unsigned number. So any new bits that are pushed in as we repeatedly divide by 2 are going to be 0s, and so at the end we end up, after 8 divisions by 2, with the same value as we started before we did the 8 multiplications by 2. So there we go. So we can use these, and let's say this rotate right command is fantastic for when we are wanting to move bits in from some of the sources, as I say, either being shifted out a different register, or if we want to set them arbitrarily, or we're using other commands that for whatever reason set the carry, and then we want to move those into a register bit by bit, then rotate left and rotate right are what we can use to do that. So there we go. So those are the rotation commands and the shifting commands that are available to us on the Z80. Now, just to finish off, one other thing we're going to look at, because I feel it's related, is our bitwise operations. Now, you may have come across these if you've ever done sort of logic gates in your hardware, which isn't something I really have any skill for, but I do remember seeing them in some project kits as I had as a kid. You might also know them as sort of truth tables and things like that. But these are basically where we are using commands that will combine two bytes and at the bit level, and the resulting bits in the resulting register, in this case the accumulator, will contain bits based on the logical result of the two commands. So we're going to look at three today here. We're going to look at AND, we're going to look at OR, and we're going to look at XOR. Now these work at the bit level and they take two parameters. One is always the accumulator, and the other in these first two cases are going to be an immediate value, an 8-bit value here, and in the third case it's going to be an 8-bit register, and these always work at 8 bits. But the result is actually calculated at the bit level. So we're going to look at AND, OR and XOR on the blackboard, and we're going to work out the logic that defines what the resulting bits will be based on the two parameters. So we've got two parameters, we'll call them P1 and P2. And then they will give us a result. Now one of these values will be the accumulator and one of these values will be the other parameter, the immediate or the register that we're processing. So this command works at the bit level, so each of these bits can only have a value of either 0 or 1, but combining the two together we'll have 4 possible combinations that we could be comparing at the bit level, and the result will be the result of those two together. Now the first command we're going to be considering is going to be the AND command. So this is going to say if parameter 1 and parameter 2 are both 1, then the result is going to be 1, otherwise it's going to be 0. Well, in this first case, parameter 1 0 and parameter 2 0, so the result is 0. In this case, parameter 1 is 0 and parameter 2 is 1, so they aren't both 1, so the result is 0. In this case, parameter 1 is 1 and parameter 2 is 0, well, they aren't both 1, so the AND result is 0. But in this one, parameter 1 and parameter 2 are 1, so the result is 1. So an AND statement will result in a 1 when both the bits that are passed in are 1, otherwise it will result in a 0. So that's our AND statement. Well, what about our OR statement? Well, it's exactly the same. So in this case, if parameter 1 is a 1 or parameter 2 is a 1, the result will be a 1, otherwise it will be a 0. Well, in this case, parameter 1 and parameter 2 is 0, so the result is 0. In this case though, is parameter 1 a 1 or parameter 2 a 1? Well, yes, parameter 2 is a 1, so the result is 1. The result is also 1 here, and of course the result is 1 here. So an OR is if either parameter is a 1, the result is a 1. Now the slightly more odd one is XOR, or EOR as it's called on some processors, exclusive OR. Now this is effectively a bit flip operation. So what it says is if the bit in parameter 2 is a 1, then parameter 1's bit will be flipped, otherwise it will be left the same. So in this case, the bit 0 is left unchanged, but in this case, parameter 1 0 is going to be flipped because parameter 2 is set to 1, so the 0 becomes a 1. Now in this case, the bit here is a 1, but it's not flipped because parameter 2 is a 0, so it's left unchanged. But in this case, the 1 here is going to be flipped because this parameter here is a 1 as well, so this becomes a 0. So you can see that it's only when the second parameter is a 1 that the resulting bit has been changed, otherwise the bit was left the same as it was at the start. So that's how the XOR command works, and as I say, this is effectively a bit flip command. Now the important thing to understand with this is we're looking at those at the bit level, but these commands actually work at the byte level. Now if we just wanted to flip a single bit, we can do so with our parameters, but the parameters we're going to be looking at and the examples are actually working at the byte level. So we're flipping sets of bits all in one go. Now here we've used a value of F0, and here we've used a value of F0, and in this case we've loaded B with F0. So we're using a mask, if you will, a mask of F0, and that's 4-bit 1s and 4-bit 0s. We can just confirm that if we go to our calculator here, and if we put in F0, which always reminds me of the Super Nintendo game, you can see that this is effectively the top 4 bits are 1 and the bottom 4 bits are 0. And the reason we're using that particular sequence is because I think it's going to make it very clear to you what these commands are doing at the bit and the byte level, and how you can make use of them in your code, which is also an important thing, because things like XOR maybe don't seem too clear to you at this stage, but as I say, I think when you start to see them in action, you will maybe understand their purpose a little bit more. So we've got this weird byte here, which is just a weird combination of bits that will we can apply an effect to and see the result. So we're going to first AND this with the mask F0. So our mask of F0 is effectively 4 ones and 4 zeros. Now our starting value, you can see here, was 57, and we did our mask of 4 ones and 4 zeros, and as I say, an AND command will keep the bits where the bit is 1 in the second parameter. So this has had the effect of keeping the 4 bits unchanged where the past parameter was 1, so the top 4 bits were 1 in our parameter, so the result in those cases is left the same. But our bottom 4 bits, well, they've been lost, so those bottom 3 bit ones have been lost, but the top 4 bits, the 0101, has been retained because of that AND command. So we've masked those bits and kept some of them based on the 1 bits in that F0, and we've zeroed some of them based on the 0 bits in that F0. And that's what we can use an AND command for, retaining parts of a byte. Now our OR command, our OR of F0, well, this will set the bits where they're 1 and it will leave them unchanged where they're 0. So our mask in this case has effectively set the top 4 bits to 1, where whatever they were before, whether they were 1 or 0, but the bottom bits have been left unchanged, and that's because of our mask of 4 ones and our 4 zeros here. So an OR command with a mask is effectively forcing the bits in our parameter to 1 and leaving the other ones unchanged. That's what that's done. Now our XOR command, again with the parameter F0, just passed through the B register here, is effectively going to flip the bits where they're 1 in our parameter, so effectively the top 4 bits. And you can see that again here. So we've got 0, 1, 0, 1, 0, 1, 1, 1. Well, the top 4 bits were 1 in our parameter, so those bits have been flipped. But the bottom bits were 0 in our parameter, so they've been unchanged. So you can see we've flipped the bits, again, based on that F0 parameter that we passed in. Those top 4 bits that were 1 have now been flipped here. So there we go. And these, as I say, these might seem a little bit odd to you, and you might be thinking, what possible use could I have for these? Well, if we go over here for a moment, well, if you're working on a black and white system like the Amstrad CPC in mode 2, you can use these for color operations. So for example, if we take this and we perform an XOR with a mask like this one here, well, we'll effectively invert those bits, and you can see that that test word is still there, but it's now inverted. And this is a great way of doing simple sprites, because if you XOR a sprite with the current contents of the screen and you do that twice, the second time will remove the sprite and it will leave the background unchanged. Now the problem with this kind of graphic is that the background will become corrupted if something overlaps it, which isn't ideal, but it's a very simple way of making a game that has background and the foreground sprites don't destroy the background. And I'm personally a big fan of them for simple games, XOR sprites, and I think that they're a lot better than people give them credit. So I would certainly suggest you consider them if you're a beginner programmer. Now, just to justify this claim that they are worth looking at, the old Dizzy games, which were fantastic, they used XOR sprites, and the Dr. Destructo game, which on the Amstrad CPC also used XOR sprites, and it was very fast and it was very good. So as I say, XOR sprites, are they the best thing in the world? No, they're not, but they aren't something you can't create fantastic games with. And as I say, they remove problems of things like double buffering when you're working out your graphics and redrawing backgrounds. So definitely worth considering. Now that's the result of an XOR, but an AND will effectively remove parts of our graphic based on a mask. And so if we mask our test here with this mask here, well, the left half of each letter has been kept and the right half has been taken away. Alternatively, an OR command here will set parts of the screen and leave other parts unchanged. So whereas an AND kept the left hand part of each character and zeroed the right hand part, the OR will keep the right hand part and it will wipe out and fill to the a yellow color, in this case, the left hand part. So, and so that's just to make the point that, yeah, while it might seem a bit obscure, why would you want to set certain bits of bytes and flip certain bits of bytes here when you're just sort of looking at these as theoretical numbers? Well, your screen is just a set of bits and bytes, and commands will be used to mask out and remove parts of your screen, or commands can be then used to add sprites over the top of those masks, and XOR commands can be used to, as I say, do simple graphics and remove them later on. So these are very useful commands that you will come to see the purpose of when you start programming and working with data coming in from hardware and having to mask out certain parts that you want to look at, or you want to change a few of the bits in a byte, maybe with an XOR, things like that. Now, one final command I'm going to discuss at this point is sort of similar to an XOR, and this is the CPL command, which stands for complement, and this effectively flips all of the bits in the accumulator. Now, this is effectively the equivalent of an XOR 255 or XOR FF in hexadecimal. So if you wanted to do XOR of all of the bits, flip all the bits, this is a smaller command. This is a single byte command, whereas XOR 255 would be a 2-byte command. And because we're flipping all of the bits, if we do this command twice, we'll end up exactly where we started, which is what this does. So here we started with 10100111. We flipped all of the bits, all the ones became zeros and all the zeros became ones. And then we did it again for some reason, and that has flipped them again, and we've ended up exactly where this started. So as I say, if you want to flip all of your bits in a register, probably don't want to use XOR FF. As I say, it will take 2 bytes. CPL will just take 1. So there we go. And that's actually the last one we're going to be looking at today. So there we go. That's the end of today's lesson. Now, we've still got lots more to cover, so please like and subscribe, because hopefully the next episode is going to be interesting to you. Next time, we're going to be looking at a few things that we've kind of missed out on so far, because we've covered an awful lot of commands, and you're really going to be starting to understand the full instruction set. But we've kind of skipped some stuff over that's very specific to things that you need to get your assembler to do, and these are a bit more specific to the assembly itself, and if you're using something other than messin, they may be slightly different on yours, but we've really got to cover them to give you the ability to work with Z80 in a full sense. So we're going to go over that kind of thing more, and we're going to look at some programming tricks that are very useful in your code, and also will help explain how you take these very theoretical commands that, as I say, you might not see a clear use for in some cases, and you can actually see them do things that will be beneficial to you if you're trying to write a game or a more complex program. Anyway, I hope you've enjoyed this today. Thanks for watching, and goodbye.